Good day, everyone. Today I'm going to speak with you about aromatic regiochemistry. First, we'll start off with oxidation and reduction of functional groups, so in particular ketones or aldehydes. Now, there's a purpose for why I'm introducing this first, and that is because as you change upon that particular functionality, whether you're oxidizing or reducing, you're changing the influence, the electronic influence of that particular structure or substrate as you move along. Okay, so that statement will make a lot more sense when we kind of delve further into regiochemistry after. So, what I want to go over with you is a few reduction techniques. I'm going to use an aromatic substrate, so this could be a hydrogen or an alkyl group. That's right there, R, so it's just some generic representation. Now, if we use a set of reagents, what are referred to as a Wolff-Kishner reduction. So you can use hydrazine, which is typically rocket fuel, and acetic acid, also with ethylene glycol as a protic solvent. And then for the second step, you use NaOH in high heat. Okay. Remember that triangle is just to denote that heat's been applied. Okay. Okay. Again, that's acetic acid. So the first step is you form something what's referred to as a hydrazone, and then by applying heat and strong base conditions, you're going to actually reduce this all the way down to a methylene carbon. Okay, so essentially you're losing that oxygen and replacing it with two hydrogens. Okay, so that's one particular example of a reduction. Another is Clemenson. So this is Wolff-Kishner reduction. And this is going to be the Clemenson reduction. Okay, so this is going to be under mildly acidic conditions followed by strongly basic for Wolff-Kishner. For Clemenson, it's just under strongly acidic conditions and the presence of a zinc-mercury amalgam. Okay, so you're going to see the same desired effect for this particular substrate because neither of these conditions make this particular ring labile. And what I mean by that is it's non-reactive. Okay, but that may be particularly important if you're thinking about, can something hydrolyze in the presence of a strong acid on this side, or can something be eliminated on this side or be reacted out? So it's pertinent that you choose the correct sort of conditions for whatever type of conversion you're doing. So this is going to be under basic conditions. This is going to be under acidic conditions. Okay. Another conversion. So notice how it's gone directly from a CO double bond to CH2 methylene carbon. There's a more mild approach using what is referred to as sodium borohydride. This is in a two-step process. So NaBH4. Okay. So this is going to be a basic reagent. Next step, you would use something like ethanol. Should be used to protonate your intermediate. So what's going to happen here is that this hydrogen is actually going to attack that, act as a nucleophile and attack that carbonyl and push those electrons up. And then hydrogen is going to be a proton source. So, and we'll get into some isotopic labeling studies later in the semester. You'll see that conversion, and I'll do the mechanism and what have you. Okay. So this could be RRS configured depending on what's there. If that R group is another phenyl ring, then it's not going to have any stereospecificity. Okay, so something to think about. Now this is the difference. Of course, it seems pretty apparent, right? So you have this OH as opposed to just hydrogens attached to that carbon. Now, this is just a one stage reduction. Okay, so the first two examples that you saw are much stronger, so it's basically two stages, right? So one stage is just adding two hydrogens here. Two stages is adding two hydrogens, so you would make a good leaving group, i.e. water, right? And you would have two hydrogens right here to get everything off, okay? And then you would, of course, have a full octet, about both of those carbons there. So there are some reducing agents. Now we will get into some oxidizing agents. Okay, so some of these will be one stage and some will be two stage. So it's, again, kind of working backwards from here to being a more oxidized form, i.e. more oxygens attached. So first, or more hydrogens removed, as it may be the case here. Okay, so we have this primary alcohol, and if we treat it with PCC, which is pyridinium chlorochromate, I believe. Yeah. Mild oxidizing agent, so it's going to just take things down one stage to where it goes from a primary alcohol to an aldehyde. Okay. So essentially just removes two hydrogens, one from here and one from here. You have a CO double bond. Okay. Aldehyde. Chromic acid's a little bit of a different story. So okay, so using the same substrate here. You see that? Good. Okay, so this conversion is, chromic acid or chromate is going to be a very strong oxidizing agent, so it's going to oxidize this all the way to carboxylic acid. Okay. Now for a secondary alcohol, it's going to be a little bit different because it's not going to remove, or it's not going to remove a C, let's say a CH3 group or some kind of R group that would be attached on the other side of this carbon that I'm referring to right here. So I'll do those conversions. But chromic acid is not going to affect that either, so it's also going to make a secondary alcohol a ketone. So PCC and chromic acid are going to yield, and at this point I hope you guys know that this is just H or an alkyl chain, whichever. Okay, so this is going to form a ketone. Okay, so primary, you just have hydrogens to work with. With the secondary, you have to have a carbon that's kept there. Okay, and chromic acid isn't as strong enough of an oxidizing agent where it's going to break that bond. You'll see KMNO4 down the line. That's going to be an even stronger oxidizing agent. So I would kind of put that from lowest to highest as PCC, then chromic acid, and then KMNO4 in the presence of base. All right, so this next exercise is just supposed to be a sort of a prediction, if you will, of what's going to be the transformation. So remember, with a secondary alcohol, if you react that with a chromic acid, you're going to get a ketone. So going for something that may be stereospecific to something that is not. Okay, PCC is going to do the same thing. In this case, it's a secondary alcohol, and it's going to go to a cyclic ketone. Okay, and then the third here, chromic acid again. Okay, so it's going to oxidize, but now that it has nothing but hydrogens at this particular carbon, it's going to fully oxidize to a carboxylic acid. So in other words, in lieu of the two hydrogens that were there, literally replacing it with oxygen right here, doubly bound. All right. Okay, then so these are all oxidations. If you haven't picked up already. And then on the right side here are reductions. So the first up is going to be Clemmensen reduction. Okay, so this is going to be a full reduction of that carbonyl to, again, a methylene carbon. Underline that. And the second example here is going to be sodium borohydride, which I mentioned earlier. It's going to be sort of a mild reducing agent. You'll see an isoelectronic counterpart, that of being lithium aluminum hydride, which is going to be more polar and hence more reactive to carbonyls, which you'll see later. But for now, we're just going to work with NaBH4. Okay, so remember, that's just going to be a one-stage reduction. So this is a two-stage reduction all the way to methylene carbon as opposed to a secondary alcohol. Okay, so you can kind of flip back and forth if you see the kind of pattern I'm going with here. Either with NaBH4 and PCC, or NaBH4 and chromic acid, at least with a secondary alcohol. Okay, so we have this final conversion. If we choose what we have above here, which is again a Clemenson reduction. So this is Clemenson. And we use those particular conditions under harsh HCl. This nitrogen, remember, those lone pairs are actually going to be slightly basic. So they're going to pick up that hydrogen at will. So that's going to be, not going to say that this won't be reactive. It's just that it's not going to be very... once you protonate this nitrogen, it's going to actually deactivate this ring. And for reasons I'll discuss in the next submodule with heterocyclic chemistry. So all of these, this whole electron network is all related. Okay. Now, something about a carbonyl, which we'll get into in module 4, is that carbonyls can either be activated or deactivated. Okay, so this carbon has electrons that are kind of pulled away from it by the oxygen right there, right? And also a double bond that's right there, so it's going to be electronegative. So it's going to be pulling electron density away from that carbon, making it more electrophilic. But you also have slightly electron withdrawing group here. Okay, so the name of the game is to get the electrons to drift up towards the oxygen because it's more electronegative. So if it's going to be fighting for the two sides, then it's going to kind of weaken the reactivity of that particular carbon, or electrophilicity, whatever you want to call it. So in this particular case, instead of deactivating the ring using something strong like HCl, you would use, with the zinc mercury amalgam, you would use Wolff-Kishner. So Wolff-Kishner again, you'd use hydrazine to form a hydrazone. Okay, and then for the next step, you would just use NaOH and heat. Okay, and that conversion is going to just look like so. I'm just going to write a phenyl ring here to keep it shorthand. Oh, I guess I can't because I have to write this out. But there's going to be a methyl group in that place. And I'm running out of space there. So that's a methyl group. Sorry if you can't see that very well. Okay, so in other words, let's reduce this down to just a methyl. Okay, so now we're finally going to get into regiochemistry here. And the first thing we're going to explore is bulk. Bulk about monosubstituted benzene ring, for instance. So I have two different substrates here. One is going to be a T-butoxy ether, and the other is going to be a cyano group. Okay, so I have two different reactions about this particular ring. Now, some of these you've seen already from the last submodule. So these are all going to be electrophilic aromatic substitution reactions. Same goes here with the nitration. Okay, so remember the H2SO4 is going to be the catalyst for those two nitrations, and then aluminum trichloride is going to be the catalyst for this Friedel-Crafts alkylation. Okay, so first conversion is right here. Now, since this T-butoxide or T-butoxy group, whatever you want to call it, is so bulky, it's going to push things to be further away, okay? And electronically, I'll kind of explain why this T-butyl group actually winds up para to where that ether resides about the ring. Okay. Now, ortho and para can kind of go hand in hand, at least from an electronic standpoint. But the thing is if this is so bulky right here, then it's going to perturb any type of coordination right there. Ortho in either position to where that ether is. Okay. That's not to say that it'll never happen. You'll just probably get that in a very low yield. So predominantly you're going to see the para. So with kinetics and chemistry, it's not a matter of if, it's really a matter of when, right? Okay. Let's take the same example now where instead of Friedel-Crafts alkylation, we're going to nitrate. So we're going to get substituted para, going to be a nitrate or a nitro group. So the nitro group is replacing that hydrogen that's down here from the substrate. And again, there's going to be a para relationship, seeing as this is just too bulky. Okay. Again, that's not to say that, not a small percentage of some of the nitrate or nitration is going to occur ortho. You just, you're looking for highest yields, right? So this is a particular type of instance where you're just going to get more para than you are ortho. Okay. Now, if this weren't a very large group at all, let's say if it was an OH group or something like that, and still electron donating, right? Remember these oxygens that are directly attached to the ring actually have lone pairs that can donate. So it will be moderately activating and electron donating. Here's the opposite, where the CN triple bond is going to be quite polar, right? So it's going to pull electron density away. It doesn't have any lone pairs to pull out, right? But it does have 3 bonds right there, and those 2 pi bonds again are going to be perpendicular to one another. Okay, so it's still a pretty bulky substituent, but this you don't have to consider so much the bulk as you consider the electronics, which is basically our next step. Okay, so a cyano group is actually going to direct that nitration meta. So remember that meta is a 1-3 relationship about a planar ring like this. Okay, so 1, 2, 3. So that's where the nitration will occur as opposed to para, like how you see there for that T-butoxy substrate. Okay, so I'm going to do a generic representation of a sigma complex. Let's say I'm going to put in an electron withdrawing group right here. Okay, and instead of, driving me nuts. Instead of putting the electrophile meta, which in your notes you can see that in figure 5 that every resonance structure or resonance form about that sigma complex or rhenium ion is you still have a stable cation. But if we put things, let's say ortho or para, I'll just put ortho. Okay. Actually, let me draw this for a second. Sorry about that. Take a lone pair right there. Yeah. Okay, so the main problem here with having the electrophile right there at the 2 position, or the ortho position as it were, is that that positive charge is laying right at the carbon where the junction where the electron withdrawing group is attached. So if it's electron withdrawing, if you remember from last semester with your electronegativity or electronegative groups drawing electrons away from a positive charge, it would destabilize that charge. Okay, so this wouldn't be very stable. So that's typically why you're going to see things meta. Okay. Now, you notice how there are 3 different forms when you look at figure 5. So let's say, for the sake of argument, we go with the pair position. And a positive charge that is there. Okay, remember these can flip down. Okay, so what's the roadblock is what's right here. In other words, this sigma complex, that sp3 intermediate carbon. Okay, so now once again, that positive charge that's EWG. Positive charge is right there where the electron withdrawing group is. So that's not going to fly either. So in other words, the best case is when you see meta. Again, refer to figure 5. In your notes. Okay, so you'll have a total of 3 different resonance structures. You'll have 3 here as well, but the problem is that you're going to have a very poor resonance contributor, if you remember that particular concept. Okay, so electron withdrawing groups are what are going to be referred to as deactivating, right? So in other words, they're not letting any electrons into the phenyl ring, right, as in this case. It's pulling electron density away. So in other words, through the inductive effect, these electrons can't reach out to anything else, right? Even a reactive electrophile, unless it's under more extreme conditions. All right, so let's go over some electron donating and electron withdrawing groups. And kind of umbrella them under each subclass here. So electron withdrawing. You have your nitro group, which is pretty powerful. You have your sulfonyl groups, which are pretty powerful. How about something that's positively charged like a quaternary amine? Okay, so that nitrogen being positively charged is definitely going to draw electron density up. So when we start to get into rings like pyridine, where that nitrogen can be easily protonated, a heterocyclic compound, it's going to be very deactivated from being positively charged or some kind of ion that's electron starved. Okay. Some other examples here. So something is slightly electron withdrawing. So this is like a pretty extreme example. If you had, let's say, chlorine or bromine or even fluorine. Okay, so they're going to be slightly electron withdrawing, but, excuse me, ortho-para directing. So these are meta-directing. And these are ortho-para directing. But weakly electron withdrawing. Okay. Okay, so why is it that they're ortho-para directing? Well, remember that you do have lone pairs about each one of these, 3 in total. So they can add to resonance stability, push some electrons around. Okay, even though they're weak electron withdrawing groups, again, they're electronegative by definition, right? So they're going to pull up a little bit of electron density in their, in their direction, but again, they're able to donate or bump an electron pair into the ring. Okay, so let's now look at some activating groups. So these are deactivating. Okay, so right here in the middle of this squiggly line, I'm just going to write hydrogen, because hydrogen's neither nor, right? It's kind of like neutral. Oops, sorry about that. Moving on over here, we have activating groups. Okay, so these are all going to be electron donating EDGs. So the ones that are weakly donating are going to be your alkyl groups. So you could just write R here. Or alkyl. I can't write this morning. Okay. So this is going to be weaker because again, they don't have any lone pairs that are directly going to throw in to the pi system. We also have, let's see here, activating OH. Okay, so the lone pair that can go in there. NH2, primary amine, secondary, even a tertiary amine. Okay, so primary or secondary or tertiary. So there are two methyl groups attached to that nitrogen on the other side of the ring, then again, that's still going to be activating. But again, when you get into the quaternary stage, that's when everything's deactivating. Okay, some other examples. So you're going to have something I didn't mention over here is something like a ketone or an ester, where the carbonyl. So I'm just going to write generically carbonyl. It's directly attached. I'll put X, or I'll put Q here or something. Okay, so Q could be OH, could also be an ester, let's just say OCH3, CH3 for ketone, H for aldehyde. Okay, so whatever's over here, that's also going to be strongly meta-directing, okay, or strongly deactivating. Remember that CO double bond is going to be very electron withdrawing. Okay. All right, so we've gone over CH3 or an alkyl chain, OH, NH2. Okay, so notice how if I put an amide here, amide I guess could go into that category as well. So the secondary amide that's attached directly to the ring, again, these nitrogen can actually go, or sorry, these nitrogen electrons can go in or out, right? So there are two ways in which it can resonate. So it's going to be weakly activating, although it's going to be activating. Okay, same thing goes for, let's say, an ester. Whatever that R group is. Okay, so again, lone pairs can either go this way or that way. And, oh, yes. And conjugate base of, let's say, a phenol, so a phenoxyanion, is going to be strongly electron donating. So that means these it has an additional lone pair that can go in. Okay. So that'll, again, activate the ring and cause things to go ortho-para. And we'll go over plenty of examples to illustrate where things are actually going to go about a ring. So just a conceptual question. You have something that's para-directing, ortho-para-directing, as well as meta-directing. What is going to be the top influence? The group that is going to be most activating. Okay, so if there's something deactivating, it's going to deactivate that particular site, whatever's meta to it, in other words. However, if there's something that's activating it at the same site, then that's going to take precedence. Okay. Again, we'll go over plenty of examples here before we kind of wrap up the concept. All right, so for 23.43, that's on page 1189, you're comparing two different monosubstituted or maybe even disubstituted rings and comparing the reactivity. Okay, so first up is example A. So you just have a methyl group on the left and then a hydroxyl group on the right. So the main difference, other than there's an oxygen here and a carbon here, is this oxygen has a lone pair that can donate in, so it's going to be more strongly activating. So OH is going to be the more activating group, therefore this particular substituent is going to, this particular substrate is going to react faster. Okay, next is D. So we have, again, toluene, and then we have nitro or paranitrotoluene here. Okay, so the nitro group is going to be in places where things would end up in the para position. So remember, for toluene, these three sites are going to be the most activated. Okay, this one's going in the trash. Okay, but here they're just two sites to activate, and notice how that nitro group is actually going to direct things in the ortho position, or at least meta to it, right? So 1, 2, 3. So in either case, this is going to be activated in more spots, and this is going to be slightly deactivating. But remember that activating overrides deactivating. So overall, this particular compound is going to be more activated. Now, again, we're talking about kinetics, fast, right? So things might occur a little bit slower right here at the ortho position relative to the pair position. So that's another thing to think about. Remember, there's not just electronics, there's also bulk. Okay. Next up is a sulfonyl, or benzene sulfonic acid, and then this thioether that you see right here. Okay, so remember that a thioether is going to be isoelectronic to an ether, right? So you're going to have lone pairs about that sulfur that can kind of go into that pi system. Okay, so this is going to be activating. This is going to be strongly deactivating. Okay, so this particular structure on the right is going to be more reactive. Okay, the last one, G. So we have two hydroxyl groups. Okay, now they may intramolecularly hydrogen bond, right, form a 5-membered ring, pseudo 5-membered ring, if you will, and then you have two methyl groups for the other option. Remember that one of these lone pairs can bond, but another, or can form a hydrogen bond, but there's another lone pair that's here that can go into the ring system. So, in other words, this is still going to be more strongly activating. Okay. So lone pairs going to beat out an alkyl group or something like that anytime. All right, so for 2346, you're simply just comparing apples to apples each time. You're just looking at different positions and where those methyl groups are going to reside about a ring, and which particular compounds are going to go faster. Okay, so what you're going to want to do is, say, assign, I'll put asterisk here, $sign here, to say all the places in which, this will influence activation. So in other words, this is going to be orthopara for each position relative to it. So we put a $sign right there, $sign right there. Conversely, remember, you're not going to substitute where these are unless you use something else and functionalize it and what have you. So we're going to put asterisk here, asterisk here. Okay, so again, orthopara, this spot's already taken. Okay, so in other words, you're singly activated on each 4 of those positions equally. Okay, whereas with the meta disubstituted, we'll put, again, asterisks above, $sign on the side here. So $sign, $sign, $sign. Okay, and then this is also going to be activating at the same spots. So which carbon is likely not to be touched? That one right there. So in other words, if these are doubly activated over here, that means that this particular 1,3 disubstituted or meta-substituted ring is going to be more reactive than the pair. Ortho. Okay, now let's look at B. So B is meta, just like we saw above here, and then para. So para, let's put $sign on the bottom. It's on the top. So again, para position's already covered. So we'll do ortho on both sides. Same goes on the bottom. So in other words, this is going to be less activated than what you see over here, like we saw from example A. So once again, the meta position is going, or the meta disubstituted ring is going to be more activated. Now we have tetrasubstituted for C for both instances. Okay, so we have 2 sites for each one. And we're going to see which one of those is going to be most activated. Okay, so this is not going to activate this particular carbon. This is not, this is. Okay, so let's say this is cents, dollars and cents, and I don't know, peace sign. Okay, so the peace sign's gonna come up right here, ortho. Okay. This should be equally activated, seeing as it's, there's an axis of symmetry right here. Let's just see how many times it gets activated. So it's going to get activated also by the cents. Is it going to be activated by the dollars? No. Is it going to be activated by that? No. Okay. So now, $sign, again, para, with respect to where that $sign methyl group is, and then ortho relative to where that asterisk is. Okay, so in other words, both of these are going to be doubly activated versus this guy right here. Say this is asterisk. Okay. And then this is going to, so this is cents, this is dollars. Not one's more contributing than the other in this case. Okay. And this is also going to be influenced by cents and dollars. Methyl positions here and here. Okay, so again, this is going to be ortho, it's going to be para. So these two are going to be even more activated than these two sites. Sites and spots is sots. Okay, so this one is going to be most activated. Okay, so in your notes I put 2349. I'm going to do a triple whammy here and add 2350 and 2351. Okay, so just through examples A through D. So the only ring among the 4 of these here that is activated is this 1,3-dimethyl or meta-dimethyl benzene. Okay, so this is going to be strongly deactivating. This is going to be deactivating. These two groups are going to be deactivating. So the only thing that's going to work for Friedel Crafts is going to be A. So that's 2351. So Friedel Crafts is good. It's a go. Okay. For nitration, that's just going to need HNO3, meaning that H2SO4 catalyst, you could use it, but it's not required for that particular nitration. Again, because this ring is going to be a little bit more activated than just naked benzene. Okay, and then and then the third one for 2350 says, should you be adding fuming fuming sulfuric acid to sulfuric acid, because that's going to act as a catalyst, or they're going to add some SO3 in there to kind of get the reaction going forward. Not necessary. So I'm just going to put not necessary. Okay. Again, because these are activated, or these are activating the ring. Okay. For the next example, for B, so you have two deactivating groups, those two ketones there that are meta-directing. So in other words, if you were to do some electrophilic aromatic substitution, it's likely to occur right there, right? So remember, these are meta-directors, so they're meta to one another, but they can only activate that particular, or direct, not activate, to this site. So okay, so is Friedel Crafts going to work? No, because these pi electrons need to reach out and pick up something else, right? So remember that Friedel Crafts is going to generate either a psyllium ion or a carbocation that's going to be most stable. So these electrons are going to resonate with some of these ketones that you see there. Okay, and then we also have, so Friedel Crafts is not going to work. Nitration, you're going to need H2SO4. Okay. It's just not, the ring is just not activated enough. Okay. And then SO3, yes. So SO3 and H2SO4 is required. Okay. And pretty much the rest is the same. So that cyano group is going to be deactivating. That sulfonyl group is going to be definitely deactivating, even though this is going to be slightly activating. Okay, so these two are going to be most activated. I would say this one's even more so. Remember that SO3H is going to be quite bulky. Okay, so in general, yeah, for all of these, you're going to have deactivated complexes for B through D, concentrated nitric acid with sulfuric acid. So that's going to be all around. Friedel Crafts isn't going to work for any of the three. And you are going to need fuming sulfuric acid. Okay, so this exercise is always a little fun if you're paying attention. Okay, so 23.53 on bottom of page 190. Okay, so you have a meta di-substituted benzene ring with two OCH3 groups. Remember, those are both activating. So they're going to be ortho-para directing. So they're doubly activating here, doubly activating here, and then doubly activating here. Okay, the main issue with what's over here in the middle is it's a little sort of a scenario of too many cooks in one kitchen, right? So there's a little bit too much bulk where those OCH3 groups are. So this site is going to be less likely. Again, it's not to suggest that it won't occur, but in terms of how fast things are going to form, if you were to do electrophilic aromatic substitution, it's going to pop around at either of the ortho positions around these less crowded carbons over here on the left. Okay, so we'll just kind of cross that particular carbon site out for a possibility. Okay, for B, we have activating, weakly deactivating. This is ortho-para directing. This is also ortho-para directing. So remember that this is going to be more influential because it's activating and this is slightly deactivating. So not once but twice. 3 times a superstar. Okay, so we have once again a scenario where things are a little bit too crowded to be right here. Again, remember this chloro group is going to be slightly larger, right? And then that OH group is going to be pretty sizable too. So to wedge things in right here, it's going to be less likely. So in other words, pretty much the same scenario that you see for A, where you're going to see some more reactivity right there on the left side of the ring. Again, both ortho to either substituent, okay? Because this is going to be slightly deactivating, but ortho-para directing, okay? And again, this is going to activate here. So there you have it. All right, for D now, so we have deactivating, meta-directing ketone, sorry. And then we have a bromo group, which is bulkier, right? So this is going to be ortho-para directing, though slightly deactivating. So remember that if this is weakly deactivating, this is strongly deactivating, whatever's more activating in general is going to be the influential piece. So this site is going to be slightly activated. This site is going to be slightly activated. It's not going to be activated over here, remember, because it's just too bulky. Remember, the bromo is going to be even larger than chlorine. Right? It's going to be take up more space since it's one stage down, or one period down, if you will. Okay, so seems kind of redundant what we're looking at here. But now that we're on F, things are going to be para-substituted instead of meta-substituted. Okay, so we have methyl group on the left here, chicken foot on the right. Okay, so chicken foot's going to be much bulkier, right? That T-butyl group. Okay, so both are ortho-para directing. So in other words, this site is probably going to, these ortho positions relative to the methyl group are going to be more activated. The reason being is because right here, remember, this is just going to have too much of an electronic presence in order for coordination to happen ortho to it. And again, both para positions are covered in this case with respect to functionality. All right, that pretty much wraps up free geochemistry. I'll do some more examples during office hours. Be sure to check those. And everyone have a good day. Thanks.